What's inside a smart microcontroller? Welcome to our channel where we dive deep into the inner workings of modern technology. In this video, we will explore what makes a microcontroller smart and how its internal components work together to power everyday devices. Smart microcontrollers are embedded systems found in appliances, vehicles, wearables, industrial machines, and more. We will break down each part, including CPU core, memory, peripherals, communication interfaces, power management, security, and development tools. By the end of this video, you will understand how smart microcontrollers function and why they are essential in the Internet of Things era. If you find this topic interesting, please like this video and subscribe to our channel for more in-depth tech breakdowns. 1. Definition of a microcontroller. A microcontroller is a single chip that contains a processor, memory, and peripherals. It is designed to perform control tasks in embedded systems. They are distinct from microprocessors because they include all necessary components on one integrated circuit. 2. The central processing unit core. At the heart of a microcontroller is the CPU core. Common cores include Arm Cortex-M, RISC-V, or proprietary architectures. The CPU executes instructions stored in memory and performs computations. Cores may support 8-bit, 16-bit, or 32-bit operations. The choice affects performance, power consumption, and cost. Arm Cortex-M cores are prevalent due to their balance of efficiency and capability. They offer multiple privilege levels, interrupts, and DSP features. 3. On-chip memory. Memory in a microcontroller includes flash, SRAM, and sometimes EEPROM. Flash memory stores the program code and non-volatile data. SRAM holds variables and stack during execution. EEPROM is used for small amounts of persistent data. 4. Power management features. Power management is critical for embedded systems. Smart microcontrollers offer multiple power modes: active, sleep, deep sleep, and standby. They may include built-in low dropout regulators, buck regulators, and brownout detection. These features help extend battery life and reduce heat. Advanced chips also support energy harvesting or ultra-low power wake modes. 5. Security modules. Security is essential in connected systems. Smart microcontrollers include hardware security modules that enable secure boot and firmware validation. They offer tamper detection, secure key storage, and crypto accelerators. Common cryptographic algorithms supported include AES, SHA, RSA, and ECC. Some MCUs include physically unclonable functions for generating unique keys. Secure elements may be integrated or offered as companion chips. 6. On-chip AI acceleration. Smarter microcontrollers support edge AI. They include neural processing units, or DSP blocks, for running ML models locally. This enables applications like voice recognition, image classification, predictive maintenance. By processing data on device, latency improves and privacy is preserved. 7. Real-time operating systems. Smart microcontrollers commonly run real-time operating systems, such as free RTOS, Zephyr, or RTX. RTOS is schedule tasks, manage resources, and handle interrupts. They enable concurrent handling of sensor data, communication stacks, and user interfaces. RTOS support also simplifies development for modular and scalable designs. 8. Development environments. Developers use integrated development environments, IDEs, like Keil, IAR, STM32Cube IDE, MPLAB-X, or vendor-provided tools. Compilers, debuggers, and Flash programmers streamline application development. Software libraries help configure peripherals, communication stacks, and RTOS. 9. Sensor integration and fusion. Smart microcontrollers often host complex sensor systems. They can integrate accelerometers, gyroscopes, magnetometers, pressure sensors, temperature sensors, ambient light sensors, and more. Sensor fusion algorithms combine inputs to estimate orientation, position, or environmental context. 10. Bootloaders and firmware update. Smart microcontrollers support secure remote firmware updates. Bootloaders check digital signatures and perform safe rollback if update fails. 11. Interconnect fabrics and bus architecture. Inside the chip, a fabric or bus connects core, memory, and peripherals. Common buses include AHB, APB, and AXI. Performance depends on bus width, arbitration, and latency optimizations. Smart microcontrollers are designed to balance high performance with low power. 12. Clocking and timing systems. Accurate timing is provided by on-chip oscillators and PLLs. Clocks can be sourced from crystals or internal RC oscillators. Smart microcontrollers support multiple clock domains and dynamic switching. This flexibility helps balance precision and energy use depending on operating mode. 13. Peripheral security and isolation. Trust zones or hardware compartmentalization allow secure execution of sensitive code. Secure and non-secure peripherals are separated to prevent leaks. 14. Debugging and trace. Debug interfaces include JTAG and SWD for program loading and debugging. Trace features capture execution history, bus accesses, and interrupt events. 15. Booting from external memory. Some microcontrollers support booting from external SPI or quad SPI flash. This allows larger applications than internal flash permits. Startup code initializes external memory controller and maps code into address space. 16. Functional safety and certification. Smart microcontrollers are used in automotive, medical, and industrial applications requiring safety standards. They may be qualified for IEC 61508, ISO 26262, or IEC 60730. Functional safety features include ECC memory, redundancy, and fault management. 17. Software libraries and middleware. Middleware stacks support USB, TCP/IP, TLS, file systems, graphics, and Bluetooth. They reduce development time and support sophisticated applications out of the box. Some vendors offer certified stacks for secure communications and cloud connectivity. 18. Edge computing and local intelligence. Smart microcontrollers operate at the edge, processing data locally instead of relying solely on the cloud. They analyze sensor data, make decisions, and communicate only essential information. This reduces latency, preserves bandwidth, and enhances privacy. 19. Future trends. Next-generation smart microcontrollers will integrate more AI and ML capabilities. They will support neural processing units with higher performance. They may offer wireless power charging, integrated FPGAs, or hardware virtualization. Software-defined features, real-time reconfiguration, and peer-to-peer edge collaboration are developing rapidly. Thank you for watching. If you enjoyed this video and want more deep technical content like this, please like the video, subscribe to our channel, and turn on notifications to stay updated with future deep dives into technology. Please leave a comment below on which feature you found most interesting. Thank you for watching, and we will see you in the next video.